The purpose of this video is to examine some ratios that involve the sides, the perimeters, the areas, and the volumes of similar polygons. Let's first of all take two squares, one of which has a side length of 2 and the other of which has a side length of 3. If we want to then go ahead and consider the ratio of their sides, remember that a ratio is just a comparison between two numbers. So in comparing those two sides, we end up with a ratio of 2 to 3. Let's now take those same two squares, but let's extend this comparison and look at the perimeters. If each side of the small square measures 2, then its perimeter is 8. And likewise, if each side of the larger square measures 3, then its perimeter is 12. So when we go ahead then and compare the ratio of the perimeters, what we find is that the ratio of the perimeters is 8 to 12. But in simplest form, that becomes 2 to 3. So then what is the relationship between the ratio of the sides and the ratio of the perimeters? Well, what we find is that the ratio of the sides is exactly the same as the ratio of the perimeters. And that leads us to the first big key idea that you need to take away with you from today's lesson. When two polygons are similar, then we know that the ratio of their perimeters is going to be equal to the ratio of their corresponding side lengths. I'm going to use a little bit of shorthand notation to notate this on my paper. I'm going to use RP to represent ratio of the perimeters and RS to represent ratio of the sides. Now this again is a big key idea, and one that although you don't need to love, you do need to memorize and know by heart. The ratio of the perimeters is equal to the ratio of the sides. Let's take this same idea, so considering the same two squares, and extend this to areas. Now the area of the smaller square is going to be 4 square units, and the area of the larger square is going to be 9 square units. So taking a look at the ratio of the sides, we get 2 to 3, and taking a look at and examining the ratio of the areas, we end up with 4 to 9. And we want to ask ourselves the same question that we asked before. What is the relationship between the ratio of the sides and the ratio of the areas? So in looking at the ratio of the sides and the ratio of the areas, the conclusion that we come to is that the ratio of the areas is always going to be equal to the square. So if I square 2, I get 4. Square 3, I get 9. So the ratio of the areas is equal to the square of the ratio of the sides. And that leads us to the second big key idea for today. Anytime you have two polygons that are similar, the ratio of their areas is going to be equal to the square of the ratio of their corresponding side lengths. And again, this one I'm going to notate using that same shortcut notation. And like the first one, this one too, you have to memorize. Now that said, I'm going to give you a little hint in memorizing. Area is measured in square units. So the ratio of the area is going to be equal to the ratio of the sides squared. All right, we're now going to extend this discussion and see what happens with three-dimensional figures. I'm going to take two cubes, again, one with side length of 2 and one with side length of 3. The ratio of their corresponding sides would therefore be 2 to 3. And I want to now go ahead and compare their two volumes. Well, the volume of the smaller cube is going to be 2 times 2 times 2, or in other words, 8, whereas the ratio or the volume of the larger cube is going to be 3 times 3 times 3, or in other words, 27. So in comparing the ratio of the sides, we still have the same 2 to 3, but when we compare the volumes, we find that the ratio there is 8 to 27. And again, we're going to ask ourselves that same question. Is there a relationship, or what is the relationship between the ratio of the side lengths and the ratio of the volumes? Well, what we notice when we compare these two is that the ratio of the volumes is equal to the cube of the ratio of the sides. So 2 cubed, or 2 times 2 times 2, gives us the 8, and 3 cubed, or 3 times 3 times 3, gives us the 27. And that leads us to the last big key idea for today's lesson. Anytime you have two polygons that are similar, then the ratio of their volumes is going to be equal to the cube of the ratio of their corresponding side lengths. And again, I'm going to represent this using some shorthand notation. This one also you need to know by heart, but this one also I'm going to give you a little trick for. Volume is measured in cubic units. So anytime I want to compare the ratio of the volumes, I'm going to take the ratio of the sides and I'm going to cube it. All right, let the good times roll here. Let's go ahead and take a look at how we can use some of these to solve some problems. So number one says we have the ratio of corresponding sides in a triangle to be 3 to 4, and they want to know what is the ratio of their areas. Well, I'm going to start with that second equation. The ratio of the areas is going to be equal to the ratio of the sides squared. And I think to myself, area is measured in square units, and that's how I can remember that formula. Well, the ratio of the areas then, simply put, is going to be equal to the ratio of the sides, 3 to 4, squared. So therefore, the ratio of our areas is going to be 9 to 16. All right, scooting along to number 2. We have two cubes who have edges in the ratio of m to n. What is the ratio of their volumes? Well, volume is measured in cubic units, so I know that the ratio of the volume is going to be what I get when I cube the ratio of the sides. So the ratio of the sides here is m is to n, and I want to cube that. And I remember that whenever I want to cube a fraction, I'm going to go ahead and multiply the numerator times itself 3 times, multiply the denominator times itself 3 times, making the ratio of the volumes m to the third over n to the third. All right, next one talks about the scale factor of two similar triangles being 4 to 5. The larger triangle has a perimeter of 25. They want to find the perimeter of the smaller triangle. Well, I'm going to remember that the scale factor is the same thing as the ratio of the sides. They want me then to compare the perimeters. Well, I know that the ratio of the perimeters and the ratio of the sides are going to be equal. So if I compare the perimeters of the two triangles, so I'm going to write a ratio then that compares the perimeters of the two triangles. It tells me that the larger triangle has a perimeter of 25. I'm going to do smaller over larger for my first triangle, or for my ratio of my perimeters. It wants me to find the perimeter of the smaller triangle, so I'm going to use x to represent the perimeter of the smaller triangle. Since I put smaller over larger in this first ratio, then when I come over here to compare the ratio of the sides, I have to remember to put smaller over larger. So I'm going to put 4 over 5. And now I can go ahead and cross multiply. 5 times x is equal to 100. That makes the value of my x equal to 20, making the perimeter of the smaller triangle equal to 20. Now, one thing I hope that you're picking up on as we go through this is that every time I approach one of these problems, I'm always going to start by writing down the little formula that I'm using. That'll keep our calculations simpler, and it'll make things easier for us as we progress through this. Number 4 talks about the area of two triangles being in the ratio of 25 to 16. It then wants us to find the ratio of their sides. So again, the first thing that I'm going to do, since it's talking about sides and areas, I'm going to write down that the ratio of the areas is equal to the ratio of the sides squared. And again, I remember this because area is measured in square units, so that exponent there is going to be a 2. So in the problem, I'm given that the ratio of the two areas is 25 to 16. They want us to find the ratio of the sides. Well, to undo squaring something, I'm simply going to take the square root of both sides. So I find that the ratio of my sides is equal to the square root of 25 over square root of 16, or in other words, 5:4. Again, the key here, take the time to write this little formula down. It will take the complicated and make it much, much simpler. All right, number 5 tells us we have a pentagon who has sides of lengths 4, 5, 6, 8, and 9. The perimeter of a similar pentagon is 24. Find the length of the shortest side of the second pentagon. So the first thing I notice about this problem is it's talking about sides and it's talking about perimeters. So I'm going to guess here that it's a pretty good bet that the formula that I'm going to use is ratio of the perimeters is equal to the ratio of the sides. Now it's not necessary to, but a lot of you will find it helpful to draw a picture. So I'm going to go ahead and draw a picture of that first pentagon. And it's not a very accurate to scale picture, but again, it gives me a picture in my mind of exactly what I'm working with here. I do know that the perimeter of my second pentagon is 24, so it would probably be helpful to know what the perimeter of this first pentagon is. So I'm going to add the lengths of all my sides. The perimeter of this guy I find is 32. So the ratio of the perimeters is just what I get when I go compare these two perimeters. 32 is to 24. And that's going to be equal to what I get when I compare corresponding sides. Well, it wants me to find the length of the shortest side of this second pentagon. Well, if I want to find the shortest side of that second pentagon, then I'm going to go ahead and compare it to the shortest side in my first pentagon. So in my first ratio, when I did the ratio of the perimeters, I put 32 over 24, or the larger over the smaller. When I come over here, in order to be consistent, I have to use the larger pentagon first over the smaller. So the side length in my larger pentagon that I'm comparing is 4. The side length that I want to find in my smaller pentagon is x. So I end up with 32 is to 24 is 4 is to x. Now if I want to, I can go ahead and cross multiply, but what I'm going to do here, just to make the math a little bit simpler and less complicated, is I'm going to simplify this ratio here first. So I'm going to dig out my calculator. 8 will go into both of those. It'll go into the numerator 4 times and the denominator 3 times. And that was a nice little simplification here, because now I don't even have to do any cross multiplication. I can automatically find that the length of that shortest side is equal to 3. Awesome. All right. Next one. Two quadrilaterals have a 1:9 ratio of their areas. What is their ratio of their volumes? Ooh, so this one is talking area and volume. Well, I have a formula that involves ratio of the areas. I know that ratio of the areas is equal to the ratio of the side lengths squared. I also have a formula for ratio of the volumes. I know that the ratio of the volumes is equal to the ratio of the side length. And again, volume measured in cubic units. So this guy is going to be ratio of the sides cubed. But I don't have one that involves both area and volume. However, if I know that the ratio of the areas is 1:9, then I can use that to find the ratio of the sides, simply by going ahead now and taking square roots. So I find that the ratio of the sides, well, the square root of 1 is 1, square root of 9 is 3. So I find that the ratio of my sides is 1:3. To find the ratio of the volumes now, I'm going to go take that 1:3 ratio and cube it. So cubing the numerator, I get 1. Cubing the denominator, I get 27. 3 times 3 times 3 gives me the 27. And I end up with a ratio of the volumes that's equal to 1:27. All right, moving along. Last one. I'm given these two similar triangles. I'm told that the area of triangle CAT is equal to 72 square centimeters. So I'm going to go ahead and label that. they want us to find the area of triangle MSE. Well, I know I'm working with areas here. I'm also working with side lengths. So the first thing I'm going to do is write down that the ratio of the areas is equal to, well, area again measured in square units. So my exponent there is going to be a 2. So if I go compare the areas, I'm going to compare the area of the larger to the area of the smaller. 72 is to x. When I go make this comparison over here for the side lengths, and since I put larger over the smaller here, I'm going to have to be larger over the smaller here. So the larger side length is 12, smaller side length is 6, and I'm going to go ahead and square that. And again, to keep the math simple, I'm going to go ahead and I'm going to simplify this ratio before I square those, but it's not necessary. You could square them, you'd just be working with bigger numbers. So 72 is to x, is 2 is to 1, and I need to square that. So on the left, I still have that 72 is to x is equal to 4 is to 1. And now I can go ahead and cross multiply. 4x's are equal to 72. That's going to make the value of 1x equal to 18. So I know now that the area of my smaller is 18 square centimeters. All right, so this is kind of a lot of information to take in. At this point, if you have any questions, I'm going to ask you to write any questions that you may have in the back of your mind down at the bottom of the page so that you can remember when you come into class the next time to ask those. And the next time you come into class, we'll be doing some practice with ratio of sides, perimeters, areas, and volumes.